Okay, so now we talk about using systems of equations, which is more than one equation that is works together, and we're going to find the solution to those systems graphically. We can do it algebraically, of course, too. We'll do that next, but graphically, and that is understanding what is a solution to a system of equations, and then looking here, a set of two or more equations with the same variables would be the system. And here, the solution is where they intersect. That would be the solution point right here. Whatever my x value is, that is my solution, or my xy coordinate would be my solution. Here, if you look, it appears we have two parallel lines. There is no solution because they never intersect. And this is intended to indicate two identical lines sitting on top of each other, which would have an infinite amount of solutions. So those are the types of solutions we can get with linear equations. And we are talking here about solving those systems. And then some of the vocabulary words here, consistent. Consistent to me indicates that we have an intersection point. I guess that's the intent, right? When we have a system that they will intersect, so that would be consistent. Inconsistent is when they do not intersect, so parallel lines are inconsistent. Independent of each other. Two lines that have different slopes will intersect somewhere on the coordinate plane if they have different slopes. So they're independent of each other because they're going to, it doesn't matter. They will intersect. Dependent though, dependent would be this line. This line has infinite amount of solutions, but is dependent that it is the exact same line. So it's just whatever you do to be able to associate the amount of solutions and the classifications. But consistent means they do intersect. Independent means it doesn't matter. They have different slopes, so they will intersect somewhere. Dependent means that they have the same slope and the same y-intercept. They're the same line. And then parallel lines are inconsistent because they do not have a solution and because they never intersect. So there you go. There's some of the characteristics. And I will just say that parallel lines have the same slope but different y-intercepts. So just to highlight that characteristic. So when I look at these equations, what do they mean? Determine the number of solutions of the system, then state whether the system of equations is consistent, inconsistent, independent, or dependent. So consistent means they do have an intersection. So solve each equation for y. Okay, so they've done their inverse operations and they said we're going to solve each equation for y because when we get it into slope-intercept form, we can make that determination whether it is parallel or not. That's a quick fix right there. We know that these two lines are parallel, but if you'll notice, they also have the same y-intercept. So those are two identical lines, just presented to you in a different form, but the same value. So when they do that literal equation and we have the same equation, we know that they are consistent, but they're dependent because they have to have the same slope and y-intercept. And because of that, they sit on top of each other. You know, we have one line and then we have another line right on top of it, and it has infinite amount of solutions infinite number of locations that it touches. So that is being able to make that determination. So here with this check, if you make both of these equations, solve for y. So when I solve both of these equations for y, I went ahead here and to isolate my y, I subtracted 3x from both sides. So I end up with negative 2y is equal to negative 3x minus 7. Then dividing both sides by the coefficient, right, that becomes 0 or 1, sorry. Y is equal to a 3/2 x plus 7/2. Then for the other equation, I have simply got to divide by the coefficient because I already have y by itself on one side, and I divide everything by 4, and y is equal to, this would be negative 3 over 2x plus 9/4. And I would say that we have the slopes are different, so it's consistent and independent, because we know it will intersect somewhere. So there we go. Now looking here for graphing, in order to graph these two equations, again, the reason we often lean to slope-intercept form is because it's the easiest one to graph by. So here we have y is equal to 5x minus 3, y is equal to x plus 5. They did their inverse operations here. So again, isolating your variable, and then dividing by -1. They came up with that. So they were able to do your literal equations to get y equals, and then when we graph it, we start off at the slope at the y-intercept, which is, in this case, -3, and then we would go up 5, 1, 2, 3, 4, 5 over 1, 1, 2, 3, 4, 5 over 1, and then that's how they graph that line right there. And then my other line was slope y-intercept of 5 and a slope of 1. This is 1 over 1, and it'd be 1, 1, 1, 1. So there you go. And then we see that those two intersect right here at 2. X is 2, y is 1, 2, 3, 4, 5, 6, 7. So they intersect at point 2, 7. So that would be my solution to those where they both are true statements. Plugging them back in, right, when my x and y is 2 and 7, 3 equals 3. Taking the other equation and plugging in 2 and 7, 5 equals 5. So both of those statements are true for both of those equations right there. Now, go ahead and graph this one. Again, I'm going to place my points into slope-intercept form first. So as I go ahead and put these in slope-intercept form, I notice that they are all even, so I just went ahead and divided by 2 right off the bat. So then I have y plus 7x is equal to -3. Move my 7x over to the other side, subtracting 7x from both sides. Y is equal to -7x minus 3. Graphing that, I start off at -3. And then my slope here is -7 over 1, or 1 over -7. So it just depends on which direction I'm trying to go. In this case, I want to go up first, so I'm going, I absolutely just did that wrong. 7 over -1, sorry, goodness. So I want to go up here, so I'm going to go positive 7, 1, 2, 3, 4, 5, 6, 7, -1. So right there is going to be my equation of a line knot. I didn't connect that very well, did I? Something like that. And then when I go to work on my other equation, I have, again, I noticed that they were all divisible by 4, so I just went ahead and did that. So I have 2x minus y is equal to -6. Subtracted 2x from both sides to try to isolate my variable. And then I have -y is equal to -2x minus 6. And since I have a negative, I want it to be positive. I just divided everything by -1, and I have y is equal to 2x plus 6. And that equation would be my y-intercept of 6, which is probably up here somewhere. And then my slope is 2. So again, my slope is either 2 over 1 or -2 over -1. So I will go down to 1, 2, left 1, 1, 2, left 1, 1, 2, left 1. So that is my other equation. So the solution set to both of these happens to be right there, which is going to be the value of -1, 4. And that is graphing that and determining the solution based on the graph. Okay, so as we continue using these systems, solving a system of equations, and what they're doing is they're giving us another possibility. So as we convert these into slope-intercept form, we've done our inverse operations, and we come up with the slope-intercept form is y equals -3/5 x plus 8 y equals negative 3 fixed x minus 4. That is going to be parallel. My slope, remember parallel lines, so the slope of negative 3.5 is parallel to the slope of negative 3.5, okay? So those are going to be, but my y-intercept is two different values. So that is why we have what would be parallel lines, because they intercept the y-intercept at two different locations. So same slope, different y-intercepts, no solution, inconsistent, because we expect intersections. And then write and solve the system of equations by graphing. Oh my gosh, it's a real world situation. How will we ever do this? Let's see. Suppose an electric car costs $29,000 to purchase, and this is how much it costs per mile to drive. A gasoline-powered car costs $19,000 to purchase, and then this is how much it costs per mile to drive. Estimate how many miles of driving the total cost of each car will be the same. According to this, if you look at this, the cost to buy an electric car is more than the cost to buy a gasoline-powered car. But it appears that an electric car is about half as much as a gasoline-powered car to drive per mile. So that's something I can derive from this problem. So writing those equations, remember my slope is something over time, and this is, in this case, over mileage. So we have this one, which is going to be the cost is equal to the cost per mile plus the initial purchase price. The gasoline powered would be those $0.08 or 8 cents per mile plus 19,000 purchase price. So when they graph those on the coordinate plane, it turns out very difficult to do for some of us, you know, to come up with these large graphs. But we can look at this and say, okay, the graphs appear to intersect at approximately 225 and 25,000 and 37,500. What that equates to is the miles. So when we first buy that gasoline-powered vehicle, it is cheaper than the electric vehicle. But due to the cost, the decreased cost in using the electric vehicle, the longer you drive it, the electric vehicle may pay for itself, or it may become cheaper than the gasoline-powered vehicle. So that's what they're saying. But at 225 miles, they break even, and they cost the same to operate. So there you go. That's what we're looking at in this word problem. And so if we plug those numbers back in, of course, we find out that, yeah, that is those two, that intersection point made those two approximately true statements. Okay. Now, using a graphing calculator to solve systems of equations, in order to put it into the graphing calculator, you do need to have it into y-intercept. And then putting it into your graphing calculator, into your y1 and y2 positions, I can go ahead now and hit graph, and it's going to appear something along this line. And then you can intersect. We're going to do a lot of this practice in class, but you use the intersect feature from the calc button. And what we do is, again, we put it into the graphing calculator. You can hit graph, or you can just go to calculate here. So using the second button to get calculate, and then find the intersect feature, and then it will find and give you the coordinates of the intersection point. And then there I'm able to find the intersection point where my x value and my y value of the intersection point. So that is my solution to those two equations. And then here, doing the same thing, solving using the system. In this case, they want the systems of equations. So we have two equations here. We have y is equal to, 4.5x minus 3.9, and then y is equal to, I'm just going to say negative 2x plus 6.5, just out of habit, and putting it into slope-intercept form. And then we can graph it and put it into the in the same fashion that we just did to find out what are my intersection points. What is the solution to the x-coordinate of the solution is that x-coordinate. So just the solution of this equation. Don't have to do inverse operations. It will give me just the solution. And here, as you can see in my graph, I have put the system into the graphing calculator. I've calculated the intersection point. So the answer here is going to be x equals 1.6. We could solve that, or we know the calculator can give us that information. We're going to have a lot of practice with this in class later on throughout the course using Desmo and the graphing calculator to come up with these solutions, but we can't just jump to that point. We actually have to practice and understand and develop those skills to where we can then take shortcuts. So with that, we're going to do a little bit more of this, but we will have tons of practice in class.